Hi again, guys. We're back at it. I hope you're well and everybody in your family is healthy. We're going to pick up with the last half of section 3, chapter 10. A little bit more math, so you need your calculator again. This is maybe a hard topic. It doesn't make sense right away, but it will, I hope, at the end. So empirical formulas, what are they? What do they show? Attached to this assignment, there's a document that looks like this for you to take notes on. If you don't want to print that off, obviously you can just take the notes on your own binder paper. You need to have the definitions in your notes, and then the steps that I'm going to walk you through. There's examples in the book that I'm using. Once we get the topic of empirical formula down, then we're going to go to something called molecular formula, which we've been talking about a lot, and how we figure the molecular formula out from empirical data. So what the heck does empirical mean anyway? Empirical means by experiment, and the empirical formula of a compound will always show the smallest whole number ratio of the atoms of each element in that compound. So whole numbers, I think, is obvious because you've got to have whole atoms. You can't have parts of atoms. But we want the lowest whole number ratio, so it's kind of like reducing fractions. The one other little thing I want to say, this is really only necessary for covalently bonded or molecular compounds. When you have an ionic formula, calcium carbonate, sodium nitrate, sodium chloride, they're always already written as they're empirical, the smallest whole number ratio. All right, now there's going to be a lot of names kind of that you've never heard of before. Some of them you'll recognize, like glucose in this example, but don't get tied up with, I don't know what that stuff is. I can't do this because I don't know what it is. It doesn't really matter. Methanol, ethanoic acid, and glucose all have the same empirical formula. Their lowest ratio of carbons to hydrogens to oxygens. So again, this is a multiple proportions thing, 3 different substances with just the same 3 elements. In ethanoic acid, it's 2 carbons for 4 hydrogens to 2 oxygens. In methanol, it's 1 carbon to 2 hydrogens to 1 oxygen. And in glucose, as you know, 6 carbons, 12 hydrogens, 6 oxygens. But you should also be able to see that 2 and 4, that's a 1 and a 2 when you reduce it. 6 and 12, 1 and 2. It's just like fractions. I know everybody's favorite thing, but you can do this. Again, everything, all 3 of these substances come down to for every 1 carbon, there's 2 hydrogens and 1 oxygen. All right, here we go with the notes. It might be easier. This is how the book set it up, but just follow along as you can. Step 1, you're going to get the mass of each element in the compound. Oftentimes we get those percent compositions, so we're just going to change the percent sign to a G for grams, assuming we have a 100-gram sample. Once you've got grams, of course, we're going to change it into moles. Easy enough to do. I think most of you are getting the hang of that. This is where it gets kind of strange, but hang with it. You're going to take and divide all the number of moles for each of the different elements by whichever number is the smallest. Hang with me, it'll make sense. Once you get to that point, you may have to round very slightly to the pennies place, hundredths place, or sometimes you have to multiply. Okay, and again, if you multiply any of the elements, you're going to have to multiply all of them to keep it proportional. It's like doubling a recipe, right? You can't just double the flour and expect to get a good cake. Once you've got whole numbers, then those become the subscripts in the chemical formulas. All right, let's try this. So here's a compound that has 25.9% nitrogen, 74.1% oxygen. And the question is, what's the empirical formula? So again, first step, change percents into grams. And you just assume that 25.9% is 25.9 grams. 74.1% is 74.1 grams. You have exactly a perfect 100-gram sample. Okay. All right. That's easy. So once you got grams, we're going to use our old friend 1 mole of nitrogen per 14.0. Notice they don't go to the hundredths place in our book very often. In fact, one of the examples, they only just go to the ones place. It won't affect your data that much. If you put 14.01 here, it's not going to change it. So 25.9 divided by 14 gives you something wonky like 1.85. 74.1 divided by 16, 4.63. Neither of these values is a whole number. Neither of them is close enough to the next whole number or the last whole number to round. So what do? Well, the next thing you're going to do is take and divide the number of moles of each by the smallest, which of course is the value for nitrogen. 1.85 divided by 1.85 obviously is 1. This number divided by 1.85, interestingly enough, comes out to 2.50. Okay, we're smack dab in the middle. Okay, so now what are we going to do? We got a whole number of nitrogens, but we've got 2.5 oxygens. You can't have 2.5 oxygens. So we still don't have the right subscripts. But this time, hopefully most of you can see, if you multiply 2.5 by 2, you're going to get the whole number 5. And obviously if you multiply 1 by 2, you get 2. Finally, those are the values that we're going to put in our chemical formula as the subscripts. For every 2 atoms of nitrogen, there's 5 atoms of oxygen. Okay, and then the last thing, of course, is to think about it. Does it make sense? Go back and evaluate the original percentages. All right, here's the example. You can do this on your note paper. If you copied off mine, there's a space for it. How do you like this compound? 1,6-diaminohexane. Oh my goodness. What the heck is that? Well, they say it's for nylon. I have no idea what it is. But I know amino has nitrogen, and hexane, you guys know, is 6 carbons with single bonds. So maybe there's something going on there. Anyway, it's really irrelevant. All you got to do is take the numbers and work with them. So the first thing, 62.1% carbon, 13.8% hydrogen, 24.1% nitrogen. Pretend all those percents are grams, right? So this would add up to a 100-gram sample. Once you change your percent sign to a G, the next step is, of course, to get grams into moles. So to do that, we divide by the molar mass of carbon, which is multiplying by 1 mole over 12.0 grams. Hydrogen is 1.01 grams per mole, so dividing by a number is the same as multiplying by the inverse. 24.1 divided by 14. Once you've got moles, you're going to divide everybody by the smallest number. So it turns out you have the fewest number of moles of nitrogen, right? We can't put a number like this for a subscript, 13.663. That's absurd, right? So obviously nitrogen's going to come out 1, and then these are going to be something else. So let's see what they come out to be. Well, this is essentially exactly 3. This is just a little bit, a few pennies off, 6 cents off of 8. It's a classic trick at the store, right? No, it's not $8, it's $7.94. It's basically 8. So we're going to assume that that number rounds to a whole number of 8. And 3 for the carbons, 8 for the hydrogens, 2 for the nitrogens. Okay, that is how this one works out. All right, how does molecular formula of a compound compare with its empirical formula? This is the second side of my note sheet if you're using that, or another page probably would be good. So definition, their molecular formulas are the real molecule's formula, the exact number of atoms that each element has in that particular compound's molecule. It's going to be some multiple of the empirical formula. It might be the empirical formula's value. It could be 2 times it, 3 times it, 4 times it. Usually it's not more than 5. Okay, and again, it's going to be a whole number multiple of the empirical formula. 2 examples, and you actually might be familiar with these compounds if you don't know their exact formula, it doesn't matter. Acetylene gas is used in welding torches. Its proper name is ethine. Styrene, like polystyrene, polystyrofoam, is they both have the same empirical formula. So these are their molecules, right? It's ethine, 2 carbons with a triple bond. Oh, there goes my vicious attack dog. And then polystyrene actually has a 6 carbon ring as well. Not that that matters. What they both have in common is they have the same empirical formula. For every carbon, there's 1 hydrogen. So 2 to 2 or 8 to 8. They're different. They have different characteristics, vastly different, but they have the same 2 elements in the same relative proportions, 1 to 1. Once you have the empirical formula that you've figured out, whether it's from data like the percent data we were using or it's given to you in the problem like this last one, you work out what the molar mass of that particular compound should be. Once you have that, then you have to be told. This has to be given to you. There's no way you're going to know it off the top of your head. They'll give you the molar mass of the actual molecule, and you calculate the empirical molecule's molar mass. All you've got to do then is divide the bigger number by the smaller number. Empirical will always be the smallest, and you get your values. Oops, sorry about that. So here we are, methanol, ethanoic acid, oops, they're out of order on the slide, and glucose. They all have the same empirical formula, CH2O. When you figure out what the empirical formula should weigh, 12 for carbon, 1 for hydrogen, that's 13. The mass of molecular mass of ethine is 26. And if you take 26 divided by 13, obviously you can see it's 2. So we put the 2 subscripts here. Benzene's molecular mass is 78. 78 divided by 13 is 6. So the 6 then becomes the subscripts for the benzene molecule. Sorry, I get the slides mixed up there. This goes back to what we were just looking at. The empirical formula mass for methanol is 30. When you calculate ethanoic acid's mass, or it's given to you, 60 divided by 30 is 2. So it's twice. 2 times 1 is 2. 2 times 2 is 4. 2 times 1 is 2. Now my cat's chiming in, sorry. And then the mass of glucose is 180 divided by 30 is 6. So 6 times 1 is 6. 6 times 2 is 12. 6 times 1 is 6. Remember, the 1's understood in a chemical formula. All right, here's a practice for you. Find the molecular formula of a compound whose molar mass is 60 grams per mole. This is given. That's the real molecule's mass. The empirical formula is CH4N. So it's always a good idea to list your known information and what you're trying to find. So step 1, calculate the molar mass of the empirical formula. That's easy enough to do. Total that all up, and we see that out to the hundredths place is 30.06, but the book kind of ignores that. So next thing you're going to do is divide the molar mass of the molecule, the molecular formula, by the empirical. So very easy to do. They gave you the 60. We calculated 30.06, which rounds to, really should be 30.1. It's not going to change it that much. And we get 2. That means the real molecule is twice as big as the simplest calculation. So now all we have to do is take the empirical formula and double all the subscripts, and we get the, oops, sorry about that, empirical formula. So this is, empirical formula is this, empirical formula mass, molar mass divided by empirical formula mass gives you molecular formula twice as big. Okay. And you can always go back and calculate the molar mass for the molecular formula and see if you did it right. All right, here's an example. I strongly suggest you stop the tape right now and try this on your own. Notice they give us 62 grams per mole. The empirical formula is CH3O. Ethylene glycol is that green stuff that you put in your radiator, mixing it with water. If we find the empirical mass, it's 31.04, but just ignore the 04 because they just go to the ones place. See if you can work it out. Stop it here. And 62 divided by 31 is obviously 2. So the real molecule for ethylene glycol isn't CH3O, it's C2H6O2, twice as big. Hope that makes sense. Hope you do okay. And stay safe. Keep working at this. I'll be putting out my grading policy very soon.